Hello everyone, this is Professor Ross and we're here to talk about the chi-square test today. Chi is a Greek letter, it looks like letter X. So that's what this whole chi-square thing is, and it's the X squared is what the name comes from. So we'll get a little more into this and talk about it, compare it to some of our other models and see how we can use it. So in our steps of statistical modeling, the very first thing we need to do is choose a model. And we've seen that there are a lot of different models we can choose. We've looked at quite a few. And the models we choose are based on the variable types we have. So far, we've always had quantitative response variables. When we have quantitative explanatory variables, then we get into regression models comparing GPA from Maryville College and high school, home prices in square feet, metal counts and latitude. We looked at a lot of regression models early in the course. When we had a quantitative response model and, response variable and categorical explanatory variables, then we've looked at ANOVA and the variations on ANOVA, birth weight and race, survival days and fruit flies, similarity scores and song lyrics, sales and display type, and or price level. So we had a bunch of ways to look at ANOVA, but it was always quantitative response, categorical explanatory. When we had a quantitative response and a mix of quantitative and categorical explanatory variables, then we looked at either ANCOVA or multiple regression, depending on the perspective. For example, amount of sales and amount of discount and brand. What's new for us now is this, a categorical response variable. So we haven't dealt with this scenario at all in this course yet. Categorical response means we're looking at a response that's typically one of two things, a positive or a negative kind of response. We can get into more complicated scenarios where it might be one of several groups, but in the examples we'll look at, basically we'll have two possible outcomes. Along with this, we're going to have a categorical explanatory variable, and this is when we know we're looking at doing a chi-square test. Note that you can also use logistic regression when a response is categorical, yes-no variable, but that's a topic for Math 222 regression. If you're interested in that, you should check that course out. You can get into logistic regression. So we've got our 4 stages of statistical modeling, lots of different models, and here's our new one, chi-square. We're going to fit the model with R as we have all along. There are going to be some necessary conditions for us to assess, and also we want to compare to a simpler model, do some hypothesis testing. And then finally, we want to use the model, interpret what it's telling us, and think about any predictions we can make. So let's get into an example. Let's say we have a study where we were looking at 3 possible treatments for cocaine addiction. So trying to help people recover from addiction to cocaine, they might have a treatment called desipramine, another treatment called lithium, and finally they might have a treatment that was a placebo. So this was a study where they used a placebo, a fake treatment. Subjects thought they were being treated, but really weren't getting anything that should help them over their cocaine addiction, as a way to compare against 2 other possible treatments. The outcome was measured to see whether they relapsed to taking cocaine again. And so we can see there's 2 categories. They're either no or yes. And this is what's called a two-way table. It shows us the explanatory variable in the rows and the response variable in the columns. So we always set it up explanatory rows, response columns, and it simply lists how many people ended up in each category. The people who took desipramine and did not relapse, there were 14 of them. The people who took desipramine and did relapse, there were 10 of those. And so that's a total of 24 people who took that treatment. We can also look at columns, for example, how many people did not relapse, 14, 6, and 4, for a total of 24 people who did not relapse, as opposed to 48 who did. Why are we choosing a chi-square test and model for this scenario. What are our explanatory and response variables? Well, our explanatory variable is treatment, and it's categorical, right? Treatment is categorical. And we've seen categorical explanatory variables before. Here's the key why we're choosing chi-square. Our response variable is relapse, and that one is also categorical. So that's the new one for us, a categorical variable as a response variable, and that's why we're choosing a chi-square. How are we going to fit this? Well, we can create this table in R from a set of data. We've got a set of data called cocaine treatment in Google Drive. If you want to pause the video and pull that up in RStudio, that'd be great. I'm going to go ahead and give the command here for how we can create a little table like this. We can create a simple table with no totals, so it wouldn't have this stuff at all. It just essentially would have this for us. And that's with just the command table. And then we tell it the explanatory variable, cocaine treatment data set, the treatment variable, comma, and then response variable, cocaine treatment data set, relapse. And so that gives us a simple table. We're going to need to use that table to do some testing with it later. It's okay. It shows you the different counts in all the categories, but it doesn't show us the totals. And there's actually a better table with some more information, but we have to install and require a new package. So it comes in the G models package. So you may want to check this out in RStudio. Go ahead and install that package and require it. And then the command is called cross table. The argument is the same. You tell it your explanatory and your response variables, and it'll give you the cross table. I'm going to show you what that looks like in R in a moment. It essentially gives us this information here, plus a little bit more. It tells us some of the percents of each group that each group is. So that's how we can create and fit the model in R. When we're going to assess the necessary conditions, there are two things we need to check for chi-squares. So we've looked at a lot of other tests. We've had 4 assumptions we need to meet. There's only 2 for chi-squares, so that's kind of nice. Number 1, our observed cell counts need to be based on random sampling of some sort. So we've got 2 different kinds of scenarios: random samples from 2 or more populations, or random assignment to 2 or more treatment groups. So you might think this for our cocaine treatment here, we would need random assignment of people into these different treatments. And then that would be one of the assumptions we would need to meet. If we have this scenario, we're looking at 2 different populations that we're trying to compare, or assignment to 2 or more treatments, then what we say is we're doing what's called a chi-square test for homogeneity. When something's homogeneous, it means it's the same. So what we're saying is we've got these different treatments. Did things turn out the same? Or we've got these 2 populations. Are they the same as far as our response goes? So that's what this one is. Later on, we'll look at one of this other type where we do a random sample from a single population classified by 2 categorical variables. And this is what we call a chi-square test for independence. We're trying to see, do the 2 variables, the 2 categorical variables, are they related or are they independent? And so that's when we're looking at a single population. Does being in one category of one variable have an association with being in one category of another variable? We'll look at an example of that later. So we need to have, but we do need a random sample. So we need some randomness involved in getting our data. The other necessary condition that we need to assess is that our sample size is large. How can we tell if it's large? If our expected counts are at least 5 for each cell. Now, let me talk about what the cells are. If you've got, for example, this cocaine treatment, I've got 6 cells. 1, 2, 3, 4, 5, 6. I've got 3 different treatments, 2 different responses, a total of 6 cells. What are the expected counts? Well, number 1, they're not these numbers. These numbers are the actual counts. When we're talking about expected counts, We're talking about what would we expect to see there based on our null assumptions. And so let's dig a little more into that in this example. First off, we mentioned since we're looking at different treatments and trying to compare those treatments and see if they have different distributions for the results, we would say this is a test for homogeneity. What are the expected counts for each cell? Well, let's pick one here and check it out. Let's look at desipramine no cell. So this cell here. What should I expect to see there under the null assumption? And the null assumption is the natural idea here that these three treatments are all the same. They're not really doing anything different for us. So this is how we think through the process. We say, okay, the null expectation is that the three treatments are the same. What proportion of the 72 people in my sample actually took the desipramine? Well, there were 24 out of the 72. 24 out of 72 is 1/3. So 1/3 of my subjects took desipramine. So now I look at my no column. I had 24 people who did not relapse. If things worked out evenly, and I had 1/3 of people taking desipramine, then 1/3 of those 24 should turn out to be in this cell. I would expect 1/3 of 24, that's 8, to show up in the desipramine no cell. 8 is greater than 5, so that's good. That means it's meeting our requirement to have at least a 5 expected count in each cell. Let's try one more. See if you can work this through for yourself. Maybe pause the video, try this out for this cell, the placebo yes cell. Can you figure out what the expected count is there? I'll talk about it in a moment here. So, what's our null expectation for our three treatments? That the three treatments all turn out the same. In other words, the amount of relapses would all turn out to be evenly balanced because I've got my three groups here that are all evenly balanced. What proportion of the 72 took the placebo? Well, 24 of the 72. That works out the same as what we saw before, to being 1/3. So 1/3 took the placebo. That means 1/3 of these 48 relapses should end up being in the placebo group. What is 1/3 of 48? 1/3 of 48 turns out to be 16. So my expected count for this cell is 16. Is that greater than 5? Indeed, so that's good. One of the nice things is you don't have to calculate expected counts yourself. R will do this for us, but I wanted you to get the sense of where it's coming from. So in R, if you what you need to do for the chi-square testing is to set up a table from your data. So I said, let's create a relapse table based on relapse here. And the command is just table, and then we just tell it, okay, put in the explanatory variable and the response variable. So this first command just creates the table. Then I set up the model with the chi-squared test command, and I give it the table I just created. And then here's how I get the expected counts. I put $expected after that model, and it spits out this. As you can tell, this is not the actual counts, right? They're different. These are the expected counts. And so I can see two things. Number one, are all of these bigger than 5? Yes, they're all bigger than 5, so that's great. I'm meeting that assumption. But the other nice thing about this is I can compare and see where things did not turn out as expected. For example, lithium turns out to be pretty close to what we'd expect. On the other hand, desipramine turned out to have a higher number of no relapses than what we'd expect. 14 is quite a bit above 8. And a lower number of relapses. 10 is quite a bit below 16. That suggests that maybe desipramine is doing better than lithium because we're having more no's, which is what we want to see, no relapses. So expected counts can help us see this. And in fact, this leads us to the heart of the chi-squared test. The heart of the chi-squared test is going to be to say, okay, if this is really what we'd expect, how can we measure how far off from those expectations we are and total that up for my whole group? All right, so let's talk about the hypothesis for that test. If we have the chi-squared test for homogeneity, which is the thing we're looking at, we have two or more populations or two or more treatment groups, then the null hypothesis is that the proportions for any number of groups are equal or homogeneous, excuse me. So, so all my groups, previously you saw, all my groups would have, for all three treatments, would turn out to have the same proportion of relapse and the same proportion of not relapse. The alternate hypothesis, if we reject that null hypothesis, we say, okay, at least two proportions are different. I know at least one of those treatments is turning out to be different than one other one. That's for homogeneity. For independence, the null hypothesis is going to be that the two variables are independent. They don't have anything to do with each other. And if we reject that, then the alternate is going to be that there is some kind of dependence, there is some kind of association between those variables. Okay, let's see how we calculate the test. As I mentioned, what we're at the heart of it is we're measuring how far off our observation is in each cell from what we expected. And so we subtract those two to see how different they are, square them so we don't have negatives, and then we divide by the number of expected so that each cell is scaled. Then the sigma says we take all those values and add them all up, and that gives us what we call the chi-square statistic. So I'm not going to make you do this by hand at all. This is what R will do for us. But the heart of it is how far off was what we observed from what we expected, and how can we cumulatively measure that? And that's what I'd like you to get from this. If the sample sizes are not small, we meet this assumption of at least expected counts of at least 5 in each cell. Then we have what is called a chi-square distribution, and we can calculate a p-value based on that distribution. And we have the degrees of freedom, the number of rows minus 1 times the number of columns minus 1. So all those are things just to give you a sense of what we'll see in our output from R. Here we can see in R we're going to do the chi-square test with that table of data we created, and we're going to tell it to turn off the correction. Correct equals false. That almost sounds like an oxymoron, right? But this correct is abbreviation for correction. And by default, R uses a conservative correction that gives you higher p-values. And basically what a lot of people say is that's too conservative. If you're meeting your expected counts of at least 5, you don't need that. So we turn it off. So then we get Pearson's chi-square test. It tells us what the data was. It gives us the chi-squared value. That's that sum of all those calculations up there, degrees of freedom. And then here's the key of what we want to see. What's our p-value? And we get a p-value, and we interpret it as usual. It's the probability of seeing the count we did if the null hypothesis is true. Really low chance, right? A low p-value, low chance of seeing the results like we did if the null is true. So the null hypothesis, that all the treatments worked out the same, we reject that. It looks like at least 2 of those treatments turned out to be different. And then we can use our model and go ahead and look and say, oh yeah, it looks like the one that was doing best was desipramine, because we're getting a lot less relapses with desipramine. So that's how we use the model. Alright, that's the heart of chi-square testing. I'm going to work through a couple more examples to help you keep getting a sense of how this works, especially the third example where we see not a test of homogeneity, but a test of independence will be somewhat slightly different. So here's another example for us, fish oil and bipolar disorder. Researchers did a study where where they gave some patients who had bipolar disorder either fish oil that contains a lot of omega-3 fatty acids, or they gave them a placebo. And then they tested to see if they had relief from their bipolar disorder. So 9 of the 14 patients experienced relief when they took the fish oil. 3 out of 16 experienced relief on the placebo. That seems kind of different, huh? 9 out of 14 versus 3 out of 16. Is it statistically significant difference? That's going to be an interesting question for us. Is this homogeneity or independence? It is homogeneity. We've got 2 treatments. Whenever we're looking at different treatments and comparing them, that's a test of homogeneity. If you go into R and bring up the data set and do the cross table command, this is the kind of output you'll see. Here's the table down here, and I want to highlight some things. There's a little key here for us, the cell contents. Here's the number that turned out in each category, so that's that top number in each box. As we mentioned, 9 out of the 14 had relief in the fish oil group, right? That's our fish oil row here. And only 3 out of the 16 had relief in the placebo group. So that's what the N is. What are these other numbers in each cell? Whoa, sorry. Oh, real quick, we also have the totals, 14 and 16, right? And we had 18 who did not have relief, 12 who did, for a total of 30 in this study. The chi-square contribution is that that piece from the formula where it was the observed minus the expected quantity squared over the expected. That's what this is. And it's that measure of how far off of the expectation was this result. So it doesn't give us the expected value directly, but it tells us how far away from that expected value it was. And here's something to note. The bigger the number there, the farther off this was from what we'd expect. So our biggest one turns out to be the yeses on fish oil. There were more people experiencing relief on fish oil than we would have expected. That's what that higher number is there. Closer to 1 means it's closer to what we would have expected to see. The next are proportions. So the next number gives us the proportion of the row total that this value is. So for example, 5 is 35% of these 14. Right, and 9 is 65% of these 14. The next one down is the column total. So 5 is 27% of these 18 that did not experience relief. And you can see, for example, 13 is 72% of the 18. And then lastly, it's the percent of the total. So 5 is 16% of all the 30 people in this study. You can also see percents for the columns. 18 is 60% of the, of the 30, right? 18 is 60% of the 30. And likewise, for example, 16 is 53% of the 30 total. So that's a really handy table. With that cross table command, it gives us lots of great information. We can check if we meet our assumptions. There's 2 assumptions to beat. First, do we have enough expected, high enough expected value in each cell? So we can store a table and then do the chi-square test with the expected tag on there, and it'll give us expected. And the first question is, are each of those at least 5? And if we look, yes, 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 we have met that assumption. The other assumption we need to meet is, did we have some kind of random assignment or random sampling here? And we don't have all that information here. We would want to dig a little bit deeper and find out, how did they assign these patients to getting fish oil or placebo? If that was a random assignment, then we have met that other assumption. And for now, let's go ahead and assume we've got that. I also have on this screen put the actuals in here as a nice way to do some comparing. For example, the fish oil, we would have expected 5.6 people to see relief, right? Not exactly 5.6. It'd have to be 5 or 6, right? We actually saw 9. Wow, that was a lot higher than what we expected. Or we had expected only 9.6 people to not have relief on placebo, but it turned out to be 13. Oh man, more people did not have relief on the placebo than we would have expected. So comparing your actuals to expected gives you a sense of what's going on. We can test this and say, are these differences statistically significantly different? And once again, we run the chi-square test. It gives us results. Here's the statistic. The key is we want to look at the p-value, and we've got a low p-value. So we reject the null hypothesis. And for a test of homogeneity, the null hypothesis is that things are homogeneous. All the treatments are the same. So here we say, not all treatments are the same. Here there were only 2 treatments. So really what we're saying is fish oil was not the same as placebo. It looks like there was more relief for bipolar disorder for the people who took the fish oil. There are a couple other things to think about here. It appears that fish oil works, but is there a meaningful difference? So we've found times where there's a statistically significant difference and not a meaningful difference. Well, the fish oil saw 64% relief. The placebo saw 19% relief. Does that seem like a meaningful difference? It does to me. That's a lot more people seeing relief from fish oil than from the placebo. So it does look really promising. There was one thing they reported that might be problematic that we should think about. The original article noted that some participants reported a fishy aftertaste after they took their pill. Now, they did not know what they were getting. It was what's called a blind study, but they thought they might have had some fishy aftertaste. Why might that be a problem? The thing we need to be concerned about is what's called the placebo effect, where an expectation of improvement can lead to actual improvement of health. So here, they took these things and they said, whoa, they taste kind of fishy. This must be some real powerful medicine they're giving me. And now I'm feeling way better. And so that's what the placebo effect would be all about. Your goal would be to maintain a blinded study where if it's a single blind, the patients don't know their treatment. They're taking pills. They don't know if it's a placebo, is it fish oil, is it something else. That way, they wouldn't experience the placebo effect. A double blind is even better, where the patients don't know what they're getting and those treating the patient don't know what they're getting either. They just say, hey, here's some pills for you to take. I don't even know what's in them. Now, how can that work out? Well, someone up the line, someone coordinating the whole project knows what each person is getting, but the person handing them the pills doesn't know, and that means they can't really give anything away either, because they don't know what's going on either. So there may have been some placebo effect causing some issues here. On the other hand, though, this is a really big difference. And so when we use this model, we can see that it does appear to be a meaningful difference, and we would definitely want to dig in deeper and see if we can find out more about what's going on. Last example I want to talk about for a couple of minutes, the stand your ground conviction rate. So stand your ground law, someone can use whatever force they deem necessary to protect themselves in a place they have the right to be. Some states have this kind of law, but it's rather controversial. Many people who have committed violent crimes actually have tried to claim that they were standing their ground. They had a right to be there. They had whatever force, they used whatever force they deemed necessary to protect themselves. And sometimes it seems like they're using it to cover up use of violence, or they're using excessive violence when they didn't really need to. In this scenario, we're going to talk about defendants. That's the person who actually used violence. They're the ones who's saying, I deemed it necessary to use this violence to protect myself. And we're going to look at defendants who are white. We're also going to talk about victims. This was the person who was injured by that person's violence. So the defendant thought the victim was attacking them. They defended themselves with violence. The victim is the one who actually got injured or even killed. We're going to look at victims that are both white and not white. So we're interested in the question, are white defendants convicted at the same rates when victims are minority as when victims are white? We believe we can detect racial bias by looking at these conviction rates and seeing if they're the same or if they're different. Is there a connection between whether the white defendant is convicted when the victim is white versus when the victim is a minority? Racial bias would be indicated by having a higher conviction rate when the victims are white, because that would mean a lower conviction rate when the victims are minority. In other words, the force that they deemed was necessary seemed to be an okay thing because the person they thought was attacking them was a minority. Oh, that's just fine. Versus if the person attacking them was white, then they'd say, whoa, no, you shouldn't be using force against a white person. So that's the kind of thing we'll be looking at for racial bias. So let's check out the numbers here. Once again, in R, we can create a table like this. And we've got 118 cases that were chosen to be analyzed here. All of the defendants were white, but the victims were either minority or white. And you can see that out of the 21 cases where the victim was minority, we had 3 convictions. And out of the 97 cases where the victim was white, we had 35. It's a little bit hard to tell from just looking at these straight up numbers if that's an important thing there or not. Why? Because 21 is pretty different than 97. So what we'd like to know is, what's the percent of the row, rather than looking at 3, looking at 14 versus 36. There's a lot lower conviction rate against a white defendant when the victim was a minority. Is that a statistically significant difference? That's what we'd like to find out. First, is this a test of homogeneity or independence? Well, we do not have different treatments here, minority and white. Those are not treatments. And we don't have different populations either. What we're looking at is one population, all these cases, and we're looking at 2 variables and asking, are they connected? Is the race of the victim connected to the conviction? Is there independence there or dependence? So it's a test of independence. We can check out expected counts just as we have before with the chi-square test. Why would we want to do this? We want to see if we meet our assumption. Do I have at least 5 in each of these? Good to go there. What about our assumption of random sampling? We would need to dig a little bit deeper here, but if they did a random sampling of these 118 cases, then we're good to go there as well. Do we need random assignment to minority or white? No, that doesn't make any sense. In this case, it's not like a treatment, and we're not looking for homogeneity. The hypothesis test itself, we've seen how to run that in R, and the big thing we want to look at is p-value, and we have a p-value that is right on that borderline. Usually we say 0.05 is the cutoff, and we are right at that cutoff. What should we conclude? Well, we have at least moderate, maybe nearly strong evidence against the null hypothesis. So the null hypothesis says these 2 variables are independent. I'm going to jump back here. Victim, conviction, independent. We have moderate evidence against that. It's not strong. We're not saying, whoa, clearly that's wrong, but it suggests that perhaps it's not true that these are independent. We're kind of right on that borderline. What would I do in a case like this? I would love to go back and try to get a bigger sample. See if I can get some more cases in there and see if the picture clarifies some. We at least have marginal evidence that the conviction rates differ, that there might be some racial bias in the court system here. Could we conclude cause and effect? Is it the race of the victim that is causing a difference in conviction? We would need random assignment to, random assignment to the race of the victim. And of course, we can't have random assignment to that. So we can't conclude cause and effect. That means there might be confounding variables. Can you think of something that might be related or connected to the race of the victim and the conviction? You could probably think of a few things, right? We might have the race of the members of the jury, or the race of the judge or the lawyer. We might have the amount of resources available to white defendants versus minority victims, and how good of a lawyer they could hire. We could probably go on and come up with lots of different confounding variables that are existing in this. So definitely a scenario where we'd want to do some more digging into this and seeing if we could find out more about what's going on. So that's chi-square testing. When we have a categorical response and a categorical explanatory, both of them categorical, we can do chi-square testing. We do that same process of choosing the model based on the variables, fitting it with some statistical software, assessing our conditions, and testing the hypothesis for a simpler model, and finally using the model to make some conclusions.